and thanks a lot for bringing together, organizing this very nice event. So since I understood that the audience, the background will be very different, I will try to be as pedagogical as possible, but please interrupt me at any point also if you want more details that maybe I will not mainly focus on. So yes, the main topic is this quantum version of this anomalous, quite counterintuitive effect known as Mpemba effect. And all the results that I will present you are actually based on a recent review that we finished with Filiberto Ares, who is postdoc in SISSA, and Pasquale Calabrese, who was my PhD advisor. Yes, let me start. I will not mention so many references. So then, if you're interested in more details, just please ask me. Okay, so maybe a bit of let's say historical introduction to the topic. What is this Mpemba effect? And I think it's worth mentioning that actually this phenomenon goes back to the ancient Greeks, to Aristotle, who wrote in his Meteorologica, to cool hot water, begin by putting it in the sun, which is already something quite counterintuitive, now that you wouldn't believe. And there have been some other, let's say, words, thoughts along this line. But the name, let's say, Mpemba effect, was only given actually much later, in the 60s, when an high school student, Erasto Mpemba, was preparing an ice cream. And at least this is the story that I read. So he was preparing this ice cream together with some friends, but he was late. So he prepared this solution of boiled milk and sugar, and he just put it in a kind of refrigerator of the 60s. What he realizes that this ice cream was ready before then the ice cream of his friends. So, of course, this was quite counterintuitive, and he asked for explanations to the high school teacher, but no one had some clear answer until a physicist, Osborne, visited the school and decided to make an experiment to check whether this observation was true or not. And this experiment was done using water. Indeed, the main, let's say, the main sentence summarizing this Mpemba effect is hot water freezes faster than cold water, which is quite counterintuitive, and it's a phenomenon that happens mainly when you have, let's say, something that suddenly happen in your system. No, it's not what you would expect if you have some, let's say, adiabatic cooling of the system. And on top of this, nowadays, the fact whether this Mpemba effect occurs or not in water is still under debate. So it's not clear whether it occurs or not. Apparently, many people in the community think that it's actually more an artifact of the impurities of the system, so not really a property of the water itself. And beyond, let's say, these historical remarks, I have to say that since the 60s, there have been a lot of works trying to understand better when this Mpemba effect occurs, in what kind of systems, what is the mechanism behind it. And for instance, this is a plot which is taken by this work by Kumar and Beckhofer, where they observe this Mpemba effect in a colloidal system. And so what do I mean by Mpemba effect in this case? So we have the colloidal systems taken from two baths, one at hot temperature and the other at warm temperature. And they relax, and this distance basically measures the distance between the probability distribution taken at a given time, and the probability distribution of the equilibrium distribution, so the Boltzmann distribution, represented by this black line. And the fact that this probability distribution in red reaches the black line before then the blue one, so inducing this crossing, is basically the main signature of the presence of this Mpemba effect. And for this specific class of systems, which are classical Markovian systems, there is also a theory behind, which was developed some years before in this work by Lu and Rax, where basically they built a theory that was able to predict a priori whether these Mpemba effects, so whether this crossing occurs or not, by studying the Fokker-Planck equation describing this phenomenon. So this is just to say that from the ice cream and water, this phenomenon has been studied in a lot of different settings. Here I'm showing this experiment involving colloidal systems, but there have been studies involving spin glasses, granular gases, polymers, really, let's say, a lot of fields. And when I was preparing this talk, I was just Googling like Mpemba effect, and also, let's say, on standard magazines, you can find, for instance, this was an article about the inverse Mpemba effect, when rather than let's say hot water freezes faster than cold water, basically the opposite occurs, or other nice pictures always involving water. And then more, let's say, on the scientific side, I want to mention that recently another review has been done about this mainly about the classical version of the Mpemba effect, and this appears on the archive basically a few days before ours. So lots of activity, lots of research going on in the classical physics. And so it's natural to ask, what about the quantum counterpart? So a setup in which quantum fluctuations are non-negligible. And this is something that I will mainly focus on. But of course, we were not the first one trying to address this question. And a quantum counterpart of the Mpemba effect was studied even before us, mainly in open system. So this is an example of a definition of the quantum Mpemba effect in open system introduced in this work by Lesanowski. So the setup that they studied was the following. They started from an initial pure state, rho zero, that then evolves according to an open quantum dynamics. So rather than, before I said the classical Mpemba effect is understood in Markovian systems described by a Fokker-Planck equation. Here, basically, you just have to flip the classical with the quantum counterpart of the Fokker-Planck equation, which is the Lindbladian equation. And in principle, you can write the solution to this equation as an expansion in eigenmodes. And for a generic system, all the eigenmodes will contribute to the relaxation, to the dynamics. However, what they proved in this paper was that it exists a unitary operator, U, that once you apply to the initial state and then you let the system evolve according to the same Lindbladian, basically the effect of this unitary operator is that it kills the slowest eigenmode of the solution of the density matrix. And so basically, if you compute a given observable as a function of time, if this observable, let's say, corresponds to the solution of the standard Lindblad equation, it will have as lowest relaxation. While the fact that you perform this unitary on the initial state, and so you kill somehow the slowest decay eigenmode, is responsible for the fact that the same observable approaches the stationary value faster. So again, you can see this crossing that, as I said, is a signature of the Mpemba effect. And in this case, they have a kind of strong version of the Mpemba effect, where they're able to engineer this kind of rotation in order to speed up the relaxation to stationarity.
Can
So
I
this
ask a
is
very stupid? Can I ask a stupid question? Like it's a
yeah,
bit like
sure.
cheat. It's for me it sounds like cheating because you're evolving
It's a
with a
bit
unitary. It's like you're evolving your state somewhere else. So it's like there is actually some time that has already happened, and then you
yeah,
start them at
let's
the
say
same
it's
time.
you're right, you're right. It's a kind of engineer Mpemba effect, but
Okay.
maybe it's better if you think of it as like, for instance, suppose that you want to prepare some state, no, and you have a target stationary state. Then
Hmm.
this way of proceeding is a kind of, I mean, gives you a kind of knob such that you know that you will get to that stationary state faster.
Okay.
So
Okay.
it
Okay.
can help. It can have, let's say, some applications also where it's useful to have this.
Okay. I see. Yeah, okay.
And also, I think one of the motivation for them to engineer it in this way was because also in the classical physics there was this strong version of the Mpemba effect. So basically, what they did was to simply, let's say, engineer simply was to engineer the quantum version properly, proving the existence of this unitary operator. At least this is my understanding of this version of the Mpemba effect. Because, as I said, as you saw, the title was quantum Mpemba effect, because indeed there is a plethora of Mpemba effects. So, for instance, this that I've presented now concerns mainly open quantum system, but also in the setup of open quantum system, there is also this work by Andrea Nave and Michele Fabrizio, where basically they engineer a temperature quench similar to the one that we saw before in the classical setting, but just in a quantum setting, where basically if the temperature becomes too low, then the quantum fluctuations become too relevant. And so they were trying to detect, let's say, the impact of these quantum fluctuations in a setting more similar to a classical setup. And I won't give more references, but there are a lot of, let's say, way to try to understand and observe, engineer this quantum Mpemba effect that we can summarize as follows. So the way in which it occurs is when the more the system is out of equilibrium, the faster it relaxes. So let's say that before I was talking more like hot water, if it is faster than cold water. But if we want to really formalize it in a more, let's say, physical framework, then the way in which we can refer to it is this one. The more the system is out of equilibrium, the faster it relaxes. Now, the main focus for us was to observe, let's say, a quantum version of the Mpemba effect, but in closed systems. And to look at closed systems, actually, it's important not to look at the system as a whole. Like if I have A and B that form an out of equilibrium isolated quantum system, what I should do is to look at, let's say, locally what happens in my system. So I have to define the reduced density matrix, which is simply obtained by taking the full density matrix and tracing it over a region B that now is acting as a bath, let's say, on my system A. And the reason for this is that if I have a system and it evolves according to with a unitary dynamics, then the system itself doesn't thermalize. So I have to look at something local that can thermalize to a Gibbs ensemble or to a generalized Gibbs ensemble, depending on the kind of system that we are dealing with. And one can properly define the notion of stationary state by observing that an isolated infinite system relaxes a stationary state if for any subsystem A, this limit exists. So this definition of, let's say, a stationary state allows us to study the quantum version of the Mpemba effect, also in isolated system, but by looking for, let's say, an observable, a metric that now depends on the subsystem. So before I was talking about the total density matrix, because anyway, we were dealing with a mixed state because I was considering an open system. Now I have an isolated system. And so if I want to introduce the notion of, let's say, distance from a thermal state, I necessarily have to look at local properties. And so the question is, what is a good metric that shows these crossings, this distance from the stationary state? And this will be indeed the first point of the rest of the talk after this, let's say, introduction to the topic. And this distance is what I will call entanglement asymmetry. Then I will show how the entanglement asymmetry can probe this quantum Mpemba effect in closed systems. And I will also present some results from an experiment done using trapped ions in order to, let's say, show that it's not just an artifact of some analytical or numerical simulations, but it can be also practically observed. Then I will try to show what is the microscopic origin of this phenomenon, especially for integrable systems. And finally, I will draw some conclusions. So again, feel free to interrupt me at any point. Okay, so let's start from the definition of my metric. So what I will use in order to detect my quantum Mpemba effect, and not only because, to be honest, the main motivation for which we introduced it wasn't the Mpemba effect. I mean, the Mpemba effect, it's something that we observe later. So just to be on the same page, let me define the setup. I will consider usually a one-dimensional system. You can think of it as the ground state of a spin chain, or some one-dimensional state described by a density matrix, rho. And as I said, I have to focus on a subsystem. So I will refer to rho A as the reduced density matrix, describing the properties of the subsystem A. And the other important character involved in the game is a charge. Now, in the case in which my state psi is an eigenstate of this charge, like for instance, the magnetization of the number operator, so a generator of a UN symmetry. If the charge is local, meaning that I can split as the charge in A plus the charge in B, from the commutation relation between rho and Q, using the fact that the charge is local, once I trace this commutation relation over B, I find that a similar commutation relation holds at the level of the subsystem. And so what this implies is that this reduced density matrix is diagonal in the eigenbasis of the charge restricted to the subsystem A. So this is let's say how it would look like the reduced density matrix in the eigenbasis of Q of A. So each of these blocks is labeled by an eigenvalue of the charge restricted to Q of A. And in principle, okay, one can ask what is the entanglement in each of these charge sector, and this was under the name of symmetries of the entanglement, which is something that I studied during my PhD. And indeed, it was the starting point to introduce the entanglement asymmetry because starting from this structure that the reduced density matrix has in the presence of a conserved charge, then one can ask what happens if rho of A and Q of A don't commute. So I will call it charge, but indeed it's not a charge in the sense that it doesn't generate any symmetry. Because now rho of A and Q of A, the symmetry is broken. Rho of A and Q of A don't commute. So it means that if I try to write down rho of A in the eigenbasis of the charge Q of A, it will have some out of diagonal element. And so my question is, how much the symmetry is broken? Like, what can be a quantity that takes into account how much this symmetry is broken? And I want to do this beyond a simple order parameter, because in principle, the order parameter also tells me if the symmetry is broken, but the vice versa is not always true. And especially the order parameter is characterized by, for instance, oscillations. We didn't want, we wanted something less local and more robust. And so to address this question, we introduced this notion of entanglement asymmetry, again, together with Filiberto and Pasquale, and it's defined as follows. So I have my reduced density matrix, rho of A, which has this block diagonal structure plus these out of diagonal elements. Then I symmetrized my reduced density matrix, rho of A, in such a way that only these blocks remain. And the entanglement asymmetry is nothing more than the difference between the entanglement entropy associated to my symmetrized reduced density matrix and the entanglement entropy associated to my original reduced density matrix. So in formulas, I can define, let's say, a Renyi version, so a replicated version of my entanglement asymmetry as the difference between the Renyi entropy of rho of A of Q and the Renyi entropy of rho of A. And in the limit tangent to 1, this can be rewritten as a relative entropy between rho of A of Q and rho of A. So relative entropy is more a kind of distance, even though it doesn't satisfy the property of being symmetric between rho of A of Q and rho of A, but still it gives an idea of how different two states are. So in this sense, the limit n going to 1 recovers the meaning of distance that one would use in order to probe how far two states are.
So this you can do only for U1, because I mean, given a system, you might have a lot of different symmetries.
No. Indeed, you can do for a generic symmetry. Indeed, I will show how to compute it for U1, and I will tell you basically what changes if you want to do for a generic symmetry.
So how do you choose? Like, then if you have different, like you can, if you have as U2, you could also choose a subgroup U1. Like, do you have a way to choose which symmetry is relevant?
No, it's completely arbitrary. For instance, it depends a bit on what you're studying, no? For instance, we were considering if you have an x-axis spin chain or a compact boson, you can vary your compactification radius such that for a specific value you have SU2, and then as you move away from that exact value, you break SU2 to U1. So in that case, it makes sense to study the breaking of the SU2 symmetry. So it depends a bit on what you want to
example
study.
is very clear. Yeah. Okay.
Yeah, indeed. I think that example is clear how you choose it. So this quantity satisfies this property of being positive. If rho of A and Q of A commute, it means that rho of A, again, will have a block diagonal structure, and so the entanglement asymmetry vanishes, as one would expect. And another comment that I want to make is that I mean, we introduced this quantity, we computed for different kind of settings, and only later we realized that actually the limit n going to 1, at least in the case in which I don't have a bipartition, so I have the total density matrix, because in principle this definition doesn't require to have, like there is no dynamics so far, so this can be defined also for the total system. And this definition with the total system actually was already present in the quantum information literature. Some literature related more to resource theory, like how to use the asymmetry of a state as a resource. So it was a literature that we didn't know, but it was nice to see how, let's say, different questions led to the same answer. Actually, for us, it was, as I will show, it's much more convenient to compute, to work with the replicated version, because it's a bit like for the entanglement entropy that usually taking the limit and going to 1, it's always a bit tricky. Well, the quantum info literature, the proper distance, the more similar, the relative entropy is closest to the kind of distance, so they were just considering the n equal 1 limit. But anyway, the idea was the same, like probe this asymmetry as a resource. Okay, so how to compute this quantity, and now exactly we'll go back to what you were asking before, meaning if I have a U1 charge, I can rewrite this the symmetrized reduced density matrix by simply using the Fourier representation of the projector, which has this form. Now, if you have a generic group and you want to symmetrize with respect to a generic group, basically you have to replace the integral over the alpha as the R integral over the elements of the group, and then you will replace this exponential with the group element to symmetrize with respect to a different symmetry. And once I have this notion of symmetrized, or once I rewrite the symmetrized density matrix as an integral, basically I can plug this definition inside. I take the n power and then take the trace, such that the trace of the n power of my symmetrized reduced density matrix can be written as an n-fold integral of these objects known as charge moments that are defined in this yellow box here. So they are basically the trace of the product of rho of A and the exponential of the charge. And since rho of A and Q of A don't commute, it's important that I keep the order. Like I cannot simply swap rho of A and Q of A, because this is exactly the tricky point of computing this kind of objects. A couple of comments about this formula. So, of course, when you swap rho of A and Q of A, meaning if they commute, then I get rid of the dependence of these fluxes here, of these alphas, because they are defined in such a way that they sum to 0. And so if the charge moments lose their dependence on alpha, basically I can put this out of my integral. This gives me 1. And so I recovered that the entanglement asymmetry goes to 0, as I would expect. And something that actually we liked about this entanglement asymmetry is that at the end, every computation boils down to compute these charge moments. And these charge moments are some functionals of the reduced density matrix with some insertion of an operator. So it means that in all the settings in which you want to compute it, you can use the same techniques that you would use in order to compute the entanglement entropy. So I don't know, if you are in a field theory setting, you can use the twist field. If you are in a out of equilibrium setting, you can use the quasi-particle picture of the entanglement or integrability techniques. So the advantage is that you can use the same techniques that you would use to study the entanglement, just take into account that now you have to insert this operator. And so from this point of view, this makes, let's say, the computation easier because we could borrow basically all the techniques that we knew to compute the entanglement. Okay, so this is the quantity that I will plot, I will show in the rest of the talk. And it's the quantity that allowed us to probe this quantum Mpemba effect. If there are no questions, I go on then in case. Okay, so what is the setting in which actually we could observe this quantum Mpemba effect? So suppose that I start from a ferromagnetic state, meaning I have some spins all pointing up. Now, this state is an eigenstate of the total transverse magnetization. And what it means is that if I compute the entanglement asymmetry for this state, the asymmetry is zero, as you would expect. Now, if I tilt my spins, I have a tilted ferromagnetic state, which is not anymore an eigenstate of the charge. So this commutation relation doesn't hold anymore, and the entanglement asymmetry indeed is different from zero. And in this case, it's very simple to compute it because it's a pure state, and we can explicitly compute the entanglement asymmetry. Now, rather than showing the formula, I will show a plot to explain a bit how it behaves. So it turns out that it's a monotonic function of my tilting angle. So you see that when theta is equal to 0, so all the spins point up, it's 0, as we said before. Then it increases and it reaches its maximal value when theta is equal to pi over 2, meaning all the spins pointing in the x direction. So this corresponds to the maximal symmetry breaking. And then it goes to 0 again, because indeed, let's say the setup in which all the spins point down is again an eigenstate of the total charge, just with a different eigenvalue. So it has this kind of bell shape, and we could compute for all the values of n and also take the limit n going to 1. Now, we choose this state, this tilted ferromagnetic state, as the initial state of a global quantum quench. What is a global quantum quench? It's a setting in which we start from a state at time t equals 0, and then we let it evolve with an Hamiltonian. Now, in this case, the Hamiltonian is this XX spin chain, meaning it's an isotropic version of the XY model, where basically now the Hamiltonian commutes with the charge. And so now you can ask, we have a state that at time t equals 0 breaks the UN symmetry. And then I let it evolve with an Hamiltonian that commutes with the symmetry, with the charge. You see, I call it charge even though it doesn't have the canonical meaning. Is the symmetry restored? And we compute the entanglement asymmetry in order to address this question. Here we are working in the thermodynamic limit, and then we take a subsystem of 100 spins. So the continuous lines was our analytical prediction, and the points are some numerical result. And what can we observe from this plot? So first of all, we observe that at large time, this quantity, this Reni2 entanglement asymmetry goes to 0. So it means that the symmetry is restored. And we can also compute how it goes to 0. It goes to 0 as this power law, 1 over t cube. And we can also compute the prefactor of this power law decay. And if we look at the prefactor, basically we observe that larger values of theta correspond to a smaller value of the asymmetry. This formula also suggests that larger subsystems require more time to recover the symmetry, and it is also something reasonable to expect. But then something that we didn't expect, and it's where, let's say, we started working on this phenomenon, is that the more the symmetry is initially broken, the faster it's restored. So you see, like, this red line corresponds to theta equal to pi over 3, which is larger than 4 over 5. And they said that at time t equals 0, the entanglement grows monotonically as a function of theta. So it means that at time t equals 0, I know that the entanglement, the symmetry breaking at pi over 3 is larger than at 4 over 5. But then I also know that at large time, this inversion is inverted, because I know how the entanglement asymmetry behaves at large time, and this formula says that larger values of theta corresponds to smaller value of the entanglement asymmetry. So the opposite of what happened at time t equals 0. So it means that something funny must happen in the middle, and indeed we observe this crossing here, which was our signature, let's say, of the Mpemba effect. Okay, so you might wonder, this result is true for free fermions. Of course, this was the first objection that the referee told us once we submitted the paper. And so we tried to convince them that actually this physics goes beyond simple free fermions, and we consider both a quantum quench where the evolution Hamiltonian is now an exact Z pinch chain, meaning I have this parameter delta different from 0, and if I map it to free fermions, this gives an interacting term. So it's an integrable model, but now interacting. And we observe that for any value of this parameter delta, both in the gapless, in the gap phase, this crossing can be observed. Now, these plots are done using exact diagonalization. So it means that since our total system was of 10 spins, basically there are some finite phase effects that kick in after a given time step. But still, the crossing is a feature that occurs, that happens at small time. So it's pretty visible. And beyond integrable systems, we also consider an Hamiltonian that contains some next to nearest neighbor, so a term that breaks the integrability, to observe that it's not a feature of free systems, it's not a feature of integrable systems, but it occurs also when you have this integrability breaking. And we also did some simulations beyond clean systems, so in the presence of disorder, meaning an X-axis spin chain with some disordered magnetic field. And both, let's say, if we perform an average over 100 realization of this magnetic field, both if we just look at a specific set of this disordered magnetic field, the crossing could be observed. So yes, it seems that this quantity, the entanglement asymmetry, not only is a probe, let's say, of or can measure the fact that the symmetry is restored, but quite convincingly, it can detect this phenomenon that the more the system is out of equilibrium, the faster the symmetry is restored. Now, of course, it's something different with respect to what happens in classical systems, because I don't have a single state towards which we are equilibrating, we are thermalizing. Now, the state depends on the specific initial state that I'm considering. But rather than looking at the distance between states, which would be much more tricky and complicated, we look at the property of the state that we expect should be, so the symmetry in this case, that we expect should be restored at large time. And the intuitive argument for which you might expect this symmetry restoration is that one can think in terms of a kind of Mermin-Wagner theorem, no? Like I have a one-dimensional system at finite temperature because the energy density is constant during my quench. And we know that we cannot have a spontaneous symmetry breaking of a continuous symmetry in one dimension. So in some sense, we expect this symmetry restoration on average. We have found some exceptions, but on average, we expect that the symmetry is restored. And so if I have this symmetry restoration, I can think of whether this Mpemba effect occurs or not. So this is basically how
Can I ask you something?
Yes.
So is there another way to diagnose this crossing that you can compare with?
Yes, for
Especially the
instance,
time of the crossing.
Yes, for instance, one can look at the Frobenius distance. So really the distance between like your state at time t and what you think will be the stationary state. Like usually we have used the diagonal ensemble that one can construct. And okay, we didn't do a study at the level of, let's say, the exact numerical value at which the crossing occurs, but more or less it was in the same window. And yes, you could detect also there. Now, the point is that this quantity is much easier to compute because I mean, the Frobenius distance also for free fermions is not an easy object to compute, while the entanglement asymmetry is much easier. This is why we look at this quantity. But yes, in principle, we did this with the Frobenius distance.
And the time of the crossing, do you have a theoretical prediction on how it should scale in the, I don't know, system size or whatever?
No, we don't have, let's say, a formula or a guess. What I can say is that it's for sure some early time phenomenon. It occurs, yes, beyond finances effects, beyond everything, but we don't have a formula that tells us more or less when the crossing occurs.
Thanks.
Thank you, Vito. Okay, so I hope that I convinced you that this phenomenon can indeed be found let's say in different systems. But what we try to do was also to observe it in some quantum platform. And indeed, we contacted the experimental group of Rainer Blatt in Innsbruck, and we presented the problem, and they told us that they were able to engineer the following quench. So they could prepare an initial state, which was basically our tilted ferromagnetic state. And then they could let it evolve with an Hamiltonian that is different than the one that I've shown in my first example, because it has some long-range interaction. This alpha was something like 1.2, a magnetic field. Moreover, in the, let's say, in their setup, actually they don't have a real unitary evolution, but they have really an open system. Like they have some dephasing. They have the global dephasing along the z-axis, parameterized by this constant gamma. So slightly different setting with respect to ours, and mainly due to the long range and to this global dephasing. And the question is it possible first to measure the entanglement asymmetry and then to observe this Mpemba effect? So the way to probe these, to compute this entanglement asymmetry actually is a toolbox that has been used in the last years also to compute the entanglement and related quantity, whereby entanglement, well, I should say the purity, so the second Rényi entanglement entropy, but also the negativity, the operator entanglement, the symmetries of the entanglement, so different functional of the reduced density matrix. Because the idea of the main philosophy of this, what I define this toolbox, these randomized measurements, is that basically after they prepare the state, they perform some random unitary operation on their state, and then they measure in the z basis. So the fact that they have first these random unitaries, and then the measurement is what make the measure random at the end. And then by doing some post-processing analysis, basically what they can build is a classical shadow, which is an unbiased estimator of the reduced density matrix. So it's not something based on the tomography, where people usually compute all the elements of the reduced density matrix, but what they can construct is an estimator of the reduced density matrix that allows them then to compute all the functionals of the reduced density matrix, like the entanglement asymmetry. So in this sense, the Rényi version of the entanglement asymmetry was useful not only for our analytical purposes, but also at the experimental level. Basically, this is the main plot that I want to present about this phenomenon, about this experiment. So the inset shows the data for at time equals 0. This is reminiscent of our bell shape that I was showing before. The points are the experimental data, and the solid line is basically obtained using exact diagonalization. And same in the main plot. So, Vito, to come back to your question, here, since we have dephasing, it seems that the effect of this dephasing, so this noisy that is present in the system, accelerate the dynamics, and so the crossing occurs earlier. And this is a feature of open systems. Like usually in this setting, the entanglement asymmetry doesn't decay really algebraically, as I was showing before. This was a feature of integrable systems, but it decays slightly faster. I mean, here the parameter is very small, so it's not super visible. But for open systems, there is this change in how the symmetry is restored, and indeed it's accelerated, and the crossing then is shifted.
And is there some type of threshold under which you will not have the crossing occur? In the sense that any system, every time that you have one hotter than one with higher entanglement asymmetry than the other, they will always cross. Like the one with the highest values will always cross the smallest one.
Well, for this setting, for the tilted ferromagnetic angle, indeed it depends on the initial state. Okay. I will present, I will show later, let's say, cases in which, yes, you can define, let's say, a threshold, and it's not always guaranteed that given two different states, the crossing occurs. For the tilted ferromagnetic state, yes, and this, you can convince yourself by just looking at the prediction that at the form that I showed for time t equals 0. And the fact that we have this large time prediction that tells you that basically at larger, this formula that was, this formula here. So by combining them, you can argue that, okay, for tilted ferromagnetic angles, like in this setting, there is no threshold. You will always observe it. But indeed, if you change the initial state, then it can happen that the crossing doesn't occur. And indeed, thanks for the question, because this is exactly the focus of the last part of the talk. Let's say why this happens. This is still an open question. I will try to explain why it happens in integrable systems, because, as I said, let's say a powerful feature of this entanglement asymmetry is that we can borrow what we know from about the entanglement to describe also this quantity. And so we borrow the quasi-particle picture of the entanglement valid for integrable systems in order to find this macroscopic origin of this phenomenon. And let's see why it happens. Here I'm showing two plots of the entanglement asymmetry, and at time t equals 0, I'm choosing different initial states. And in both cases, so both in the plot on in the left and the right, we see that the entanglement asymmetry of the red state, let's say, so the state 1, is larger than the entanglement asymmetry of the blue state 2. And we can rewrite the entanglement asymmetry in terms of the probability distribution of the charge in a subsystem A. And basically, it turns out that the asymmetry of the state 1 is larger than the asymmetry of the state 2 if the probability distribution that the charge is equal to its average value, so the expectation value of the charge in the subsystem A, is smaller for the state 1 than for the state 2. So in other words, here I plot the probability distribution, no? And I see that the probability distribution of the state of the red line is smaller than the probability distribution of the blue line. So it means that for the state whose probability distribution is more peaked around its average value, basically the symmetry is broken less because it's more peaked around one specific value. While for the red state, the probability distribution is more spread. So it means that there are more charged sectors involved. And indeed, the symmetry is more broken. Okay, so we have, let's say, a criterion that tells us when the entanglement asymmetry of a given state is larger than another. And in order to understand it, we just have to look at the probability distribution of the charge of the initial state. Okay. Then, in order to understand whether the crossing occurs or not, what should happen? It must happen that there exists a time step, I call it Mpemba time, after which basically this inequality basically is swapped. Because if it's swapped, it means that at time t larger than this Mpemba time, let's say the red line is under the blue line. And this occurs in this plot on the occurs in this plot on the right, but it doesn't occur on this. It doesn't occur in this plot on the left. So here I'm choosing two different initial states. The initial states are the ground state of the XY spin chain, which is a model that breaks the U1 symmetry. And so depending on how I choose my initial state, I can find the crossing or not. So now the question is, when can I find the crossing? So already at time equals 0, I've tried to argue that the amount of symmetry breaking depends on the probability distribution of the charge. Now, as we perform our quench, we can describe the motion and the dynamics of this entanglement asymmetry in terms of the quasi-particles. What are the quasi-particles? So the theory of quasi-particle of the entanglement says that when you perform your quench, basically these extra energy that you have at time t equals 0 produces some pairs of quasi-particles that move in opposite directions. And we have a contribution to the entanglement if, for instance, I monitor this quasi-particle here, and after this first time step, this pair falls, let's say, one is in A and the other will be in its complementary part. So it's creating entanglement between A and B until then it will leave the subsystem A. So this is the theory of this is the quasi-particle description of the entanglement entropy. Now, if you want to, let's say, find the corresponding quasi-particle picture for the entanglement asymmetry, basically what happens is the opposite, that two quasi-particles contribute to the entanglement asymmetry when they are both inside the subsystem A. So basically, until this time step, this quasi-particle is contributing to the entanglement asymmetry. Then, once they leave the subsystem, basically they move, they bring the charge with them, and the asymmetry goes to 0. This is why at a certain point, basically all our quasi-particles will be out of our subsystem A, and so the entanglement asymmetry simply goes to 0. And now, what are the quasi-particles? I mean, in order to understand if the blue line is on top of the red line, we have to monitor the last quasi-particles that are present in our system, no? Which are the slowest ones. And so we have to look at the probability distribution that the slowest charges don't bring any charge, because if they don't transport any charge, it means that the faster quasi-particles have already brought all the charge outside the subsystem A, and so the asymmetry goes to 0 faster. So basically, the key point is that in order to understand whether the crossing occurs or not, we have to look at the probability distribution of the slowest quasi-particles, which are the last ones that leave our subsystem. And we have to impose that the slowest quasi-particle don't transport any charge. So it means that the charge has been already transported out of my subsystem, and the symmetry is, let's say, goes to 0 then faster. Of course, this explanation relies on the fact that I have this quasi-particle description of my dynamics, which is something that happens for integrable systems, and this is why it's, I mean, it's a nice answer, also intuitive in the sense that it's related to how the charge is transported away from the subsystem, but it's specific for this kind of system. So we can say that if in the more asymmetric case, so for instance, in this red line, the charge fluctuations are transported mainly by the faster modes, so it means that the slowest modes transport no charge, then I have a faster relaxation. So the entanglement asymmetry goes to 0 faster. And so far, this is, let's say, the best explanation that we have to explain whether this phenomenon occurs or not for integrable systems. Like, for instance, for free fermions, one can really do this computation, compute these slowest quasi-particles, and relate them to the amount of quasi-particles that break the symmetry, like the correlation of the form C-dagger, C-dagger. No, that should be 0 if you have a U1 symmetry, while the correlation is non-zero if you have a U1 symmetry. So you can rewrite this probability distribution in terms of a correlation function that you see that shouldn't be there if the symmetry is once the symmetry is restored. Okay, so I think I can summarize. So we started by introducing this zoology of Mpemba effects, both in the classical and the quantum version. And I started saying that it was discovered as hot water freezes faster than cold water, but then it's been one can let's say reformulate it in more physical terms by saying that the more the system is out of equilibrium and the faster it relaxes. And I've mainly focused on a quantum version of this phenomenon that occurs for closed systems by using this quantity that I call the entanglement asymmetry. And so I hope that I've described what is this quantum phenomenon in closed systems, in which kind of settings it happens, and what are the conditions under which it can happen, partially, let's say, because as I said, the explanation was valid only in both free and interacting integrable systems, thanks to the quasi-particle description of the dynamics of the asymmetry. Now, of course, nice future perspectives that actually also recently there was a conference just on the Mpemba effect in Düsseldorf, and it was nice to see all together, let's say, people working on the classical aspect, on the quantum aspect, but still a unification. I mean, we didn't manage to find the complete unification of all these zoology. So this is something that it would be nice to do. More on the, let's say, Mpemba effect in closed systems, it would be nice to have an explanation that goes beyond the integrable case. We understand that it should be related to how the charge is transported from the subsystem, but we don't have a way to, let's say, make it formal and, let's say, write some equations that allow us to validate this intuition. Then recently I've been working a lot on, let's say, the impact that measurements have in quantum many-body systems, and also on the dynamics. So finding a possible interplace between measurements and quantum effect in the dynamics, it's also something that I would be very interested in exploring. And yes, with this, it's all. Thank you.